Welcome everyone to geometry. We want to take a look at polyhedra today. So we have a nice activity that we want to do in class. We'll get to that in a little bit, but we'll start off with some definitions, of course. Polyhedra. So polyhedra are actually a three-dimensional geometric object. Okay, so for this, we're allowing certainly a third dimension. So we have previously we saw the x-axis and y-axis that created our two-dimensional space. Not that we named the axes for this course, geometry, but what we do is we add a third axis that takes us from a flat plane to a three-dimensional space. Now, a lot can happen with that additional space, but space is used to describe it instead of plane. So now we're working in space instead of a plane. All right, so polyhedron. What is a polyhedron? Well, it's a three-dimensional geometric figure composed entirely of flat, polygonal or polygonal regions that only intersect at their sides. I'm not actually entirely sure which is the preferred pronunciation there. I've heard it both ways. So any polyhedron consists of faces, which are the regions, polygonal regions, and then the boundaries of the polygons are the edges, and the corners of the polygons are vertices. So solid figures with curved surfaces, like cylinders, cones, spheres, are not polyhedra. So a cylinder, for example, is not a polyhedra. Okay, it doesn't have this face, this one face that goes all the way around, isn't flat. It's not a polygon. Okay, so this is not a polyhedra. So some various polyhedra that we'll consider. So polyhedra is any three-dimensional geometric figure that has these qualities. Okay, just faces, edges, vertices, where the face is a polygon. Each face is a polygon. We can refine that a little bit and talk about different categories. So we have prisms. A prism is a polyhedron with two faces that are congruent and parallel. Now, what does it mean for two faces to be parallel? Well, two faces are parallel if, say, if we make it really simple here, let's say that each face was a square. Okay, so we're kind of looking at it at an angle here. If the plane that these squares lie in, right, so this square lies in one plane, this square lies in another plane. If those planes don't intersect anywhere at all, then those planes are called parallel, and these two squares that lie in two planes would be considered parallel. Of course, if we go ahead and add our edges there, then we see we have a cube. All right, so a prism is a polyhedron with two faces that are congruent and parallel. So they're the same, two faces are the same geometric figure, two-dimensional geometric figure. So they are this such that all other faces are parallelograms. Parallelograms. The other faces are called lateral faces. So you have bases and lateral faces. If the lateral faces are all rectangles, then we have a right prism. Otherwise, the prism is wrong. No, that's not what we need there. Oblique. If all of the lateral faces are rectangles, then we have a right prism. Otherwise, the prism is oblique. So here are 3 examples of prisms. And when we name prisms, we name them by their bases. So here, on our first prism, the base is a trapezoid. And if we give some labels here, we notice that the lateral faces are all rectangles, so we would call this a right trapezoid prism. Right trapezoid prism. Excellent. Here we have a 6-sided figure for our prism. These lateral faces are not rectangles, so we'll call this one an oblique hexagonal prism. And this one here, the face that we can, or not the face, but the base that we can see is a triangle. And these appear that they could be right, so we'll say that it is a right triangular prism. Excellent. So the height of the prism is the length of the segment whose endpoints lie in the planes containing the bases and is perpendicular to the planes. Whew, that's a bit of a mouthful. But what we're saying here is if we took a line, so take a point in this base, and then if we drew a line straight up until we hit the other base, and if we drew these in such a way that it is perpendicular to each base, right? They're parallel, so we should be able to do that without any problem. So we want it to be perpendicular to each of the bases, then the length of that line segment would be the height of the prism. Okay. Excellent. We won't work too much with oblique prisms, so we don't have to worry about that. In the case that it's a right prism, it's going to be just the length here. All right, so let's see here. All right, so the volume of, if we define the height of a prism to be as we have, then the volume of the prism is quite simple. It's just the area of the base, so the volume of the prism is area of the base of one of the bases times the height of the prism. Excellent. So that's prisms, and then next we have pyramids. So pyramids is another classification of polyhedron. So a pyramid is a polyhedron with a polygonal base and lateral faces that are all triangles and meet at a single vertex called the apex. If the lateral faces are all isosceles triangles, then we have a right pyramid. Otherwise, the pyramid is wrong. No, still not what we want. It would be oblique again. So let's say we have this first guy. This point here we might say is the apex. This would be the apex, and this would be the apex. It looks like it's a little bit difficult to tell by these pictures, but it looks like these are not all the same shape sides, right? They're all triangles, of course, but they're not all. Well, I suppose they don't need to be the same shape. They're not all isosceles triangles. So this one would be an oblique triangular pyramid. Excellent. This one, it looks like they could possibly all be the same shape for the triangular lateral faces. So we have a right square pyramid. Because again, we're naming these based on their base. So here, base triangular. Here, the base is a square. Square base. And here, 1, 2, 3, 4, 5 sides for the base. So that would be a pentagon. So it doesn't quite look like these are all isosceles triangles. So we'll say that it is an oblique pentagonal pyramid. Excellent. So the volume of a pyramid is connected quite nicely to the volume of the associated prism. And it makes for a nice in-class demonstration that that we won't do. We won't do this. So just I believe we would use an orange to determine this, and I'm not quite sure what that is. If I can figure it out, I'll let you know. All right, so the volume of a pyramid, if h is the height of a pyramid, so that's the height from the apex to the base, where the line segment from the apex to the base is perpendicular to the base. Then the volume of the pyramid is given by volume is 1/3 area times height, right? Where A is the area of the base. All right, so one more thing, and then we'll call this all set for this video. So we want to introduce the regular polyhedra, and in a little bit we'll take a look at Euler's formula. So much like a regular regular polygon, where we have all the same length sides and all this congruent interior angles, what we're using for a regular polyhedra are faces that are regular polygons, and all of the faces are the same. Okay, so with the tetrahedron, they're all triangles, and it's all the same triangle. For an icosahedron, same thing, all triangles, all the same triangle. Dodecahedron, they're all pentagons, they're all the same pentagon. Octahedron, again, all triangles, all the same triangle. And for a cube, we have, they're all squares. Okay, so there are only 5 regular polyhedron, and these are, or polyhedra, these are exactly it. Okay. Let's see, another nice name for them are the platonic solids, but these are the regular polyhedra. All right, so we're going to pause there for now. I'll give you a nice preview of the next video, which is just an introduction to the activity, which you'll be able to complete for the most part yourselves. All right, so I'll see you guys back here very shortly. Go have some fun.